Hey everybody, it's Thursday, October 22nd. As you can see here in the aim today, we are going to pick back up with the projectile fired at an angle problems. Specifically, we're going to talk about conceptual questions. As you saw in the video yesterday, we really got into the problem solving, at least for the most basic types of questions, and went into some conceptual questions, particularly ones that were associated with graphs. And so now that we've basically covered the problem solving and conceptual questions that you can answer with graphs, I'd like us to go back and take a look at conceptual questions that you could answer using proportional reasoning. And so if you look at the post on Google Classroom, you will see a worksheet entitled Vertical Projectile Motion, Conceptual Understanding, number 2. We already finished number 1 yesterday with the questions about the graphs. And so, again, now that we are done with the graphs, the whole point of this is to get into how we can apply these proportional reasoning concepts to answer these questions. The first one I want you to look at is the first one on the sheet, B2RT16, arrows, maximum heights. It says all the arrows shown were shot from the same height and the same angle. Though the arrows have the same size and shape, they are made of different materials, so they have different masses, and they have different speeds as they leave the bows. The question says, rank the maximum heights the arrows reach. I'd like you to take a couple minutes here to fully develop a response and an answer for the ranking. And when you hit play, we'll go over it. Okay, so as I've mentioned previously, the key to answering these questions is to coming up with the explanation first. So let's talk about the explanation first. The question here is asking you to rank the maximum heights the arrows reach. And so in thinking about how we are going to rank the maximum heights, the first thing that you should be thinking about is what is the equation for the maximum height of a projectile? And as I've tried to emphasize over the course of this topic and the objects thrown straight up in the air topic, the time-independent equation is really your go-to equation to solve for maximum height. And the reason why is because, first of all, the final velocity is always going to go to 0, and so we can just get rid of that VF squared term entirely. And then the only other unknown, so to speak, because the acceleration is a number we always know, the only other unknown in this equation here is the v naught y. And so we have delta y is equal to negative v naught y squared over 2ay. And so the obvious question here is, well, what does that tell you? And what that tells you is the maximum height, delta y, is directly proportional to v naught y squared. So, of course, we have to answer the question, well, what does that mean? And what that means is pretty simple. The object with the largest vertical component of its initial velocity will reach the largest height. End of story. And looking at the question, they don't give us that. But what they do give us, as you notice, is just the regular initial velocity. And so what we should realize here, using the equation v naught y equals v naught times sine theta, is that the initial vertical velocity is based on two things. We can say here, v naught y is directly proportional to the sine of the angle. And we've talked about those kind of questions a little bit and that kind of reasoning a little bit. And so that tells you when the angle is bigger, the v naught y is going to be bigger. And it tells you also that v naught y is directly proportional to v naught. And looking at the question, and I really like to hammer this point home because I think it's so important, looking at the question, you get super essential information in the very beginning of the problem. In the very beginning of the problem, although the picture kind of makes it look like this, In the very beginning of the problem, they tell you that these projectiles are launched at the same angle. And so essentially what that means is in this equation for v naught y, the v naught is always going to be multiplied by the same number because they all have the same angle. So the sine of the angle for all four arrows is going to be the same number. So while this is true, we actually don't care about this. And so essentially, to put all of this together here, what we are saying is not that complicated. The maximum height is directly proportional to v naught y squared, meaning the object with the largest maximum height is going to be the object with the largest vertical component of its initial velocity. And since they're all fired at the same angle, v naught y is directly proportional to v naught. So the object with the largest launch speed will have the largest v naught y, and the largest v naught y is going to give you the largest maximum height. And so that makes our ranking here C with a initial velocity of 16 meters per second, then B, and then A is equal to D. Obviously, if you put D is equal to A there, that doesn't matter. It's the same thing. And now that we've already worked out the reasoning, all you need to do is write that down. I really think this is a smart way to answer the question, because what I often see is that people who try to come up with the answer first is they just kind of squeeze reasoning into their answer instead of getting the answer from the reasoning. And so what we would say here as far as the reasoning is concerned is pretty straightforward. According to the equation, delta y equals negative v naught y squared over 2ay, the maximum height is directly proportional to the square of the initial velocity. And of course, if you wanted to write that with the symbols, that's fine, but it's easier to type here for me, and so I'm just going to do that. So according to the equation, delta y equals negative v naught y squared over 2ay, the maximum height is directly proportional to the square of the initial velocity. This means the largest maximum height will be produced by the largest vertical component of the initial velocity. According to the equation, v naught y equals v naught sine theta, for objects launched at the same angle, vertical component of the initial velocity is directly proportional to the magnitude of the initial velocity. And we'll just put here comma, so the object with the largest initial velocity will also have the largest vertical component of its initial velocity. Now, it's critical at that point to state that that's only true when they're launched at the same angle, because if they're not launched at the same angle, then that reasoning doesn't always hold up. So to finish this one off here, we just need to say, since the largest initial velocity will have the largest vertical component of the initial velocity, it will also produce the largest maximum height. And that's basically it, except we've neglected to mention anything about the mass, which they gave us. And so really, for this explanation to fully address all of the things told to us in the problem, we can just say mass has no effect on the maximum height. And that's it. Take a second to pause this video here and either write that down or amend your explanation if it's missing any of these things. And when you hit play, we'll move on to the next one. Okay, moving on with the sheet, the next question on the sheet, number 2 here, B2RT17, model rockets fired at an angle, horizontal speed at top, says the 6 model rockets shown, notice they made a mistake with that. It's supposed to be 4 model rockets, obviously. Look at them. The 4 model rockets shown are all at the same height and have just had their engines turned off. All of the rockets are aimed upward at the same angle, but their speeds differ. Though the rockets are all the same size and shape, they carry different loads, so their masses vary. Now, of course, we have a question to answer here, and that question is, what does this mean? They've all had their engines turned off. What does that mean? Well, essentially the answer to this question, and y'all should know this because you're in an airplane school, essentially this question comes down to, what does an engine do? The engine makes the thing accelerate. And so essentially what they're saying here is these objects are no longer accelerating. Effectively, we can just think of them as just having been released by the person who's throwing them. Exactly the same thing that we do for a ball. And so this question here is saying these objects which are no longer accelerating are aimed upward at the same angle, but their speeds differ, and we're asked to rank the horizontal speed of the rockets at the top, or in other words, at the maximum height. Take a second to pause this video here and work out your reasoning and come up with your final ranking. And once you've ranked them and explained your reasoning, hit play and we'll go over it. Okay, so the first thing that we should note here, and this question kind of made it easy for you, but it's still important for us to mention nonetheless, is that at the maximum height, well, I guess it wouldn't be initial velocity, but we can say Vy here equals 0 meters per second. And so because Vy equals 0 meters per second, the full velocity is just Vx. Now, it's important to realize this because the question made it easier for you by asking about horizontal speed. But if they just said speed, you'd have to realize at the maximum height, the full speed is just the horizontal component of the speed. Why are we able to say that? Because in general, the speed is made up of 2 components, Vx and Vy. And the full velocity is made up from the, as we call it, the Pythagorean sum of both of those components. We call it a Pythagorean sum because you use the Pythagorean theorem for it because they're vectors at right angles, right? And so here, the main mathematical relationship between those components is that v, the full velocity, equals vx squared plus vxy squared, and all of that under the radical. And so if the vy at that location, the maximum height, is 0, then effectively what we get here is v is equal to the square root of vx squared, which, of course, is just equal to vx. So the reason why I bring this up, even though this has nothing to do with the question, is you will see this a lot. They will give you a question like this, and it will say rank the speed at the top, and a lot of you will be tricked into picking the answer all 0 because you'll say, oh, the object stops at the maximum height. It's true if it's thrown straight up in the air, but for a projectile fired at an angle, it's still moving horizontally. And so it's not stopped. It's only stopped in the vertical direction. It's still moving horizontally. It still has a horizontal velocity. So looking at the actual question that's being asked, they're asking us to rank the horizontal speeds at the top. Well, the first thing that you really need to realize to answer this here is that the acceleration in the x direction is always 0. And so that means the horizontal speed of the rocket stays constant. And so that means whatever point you're talking about, this is really the only equation that you have to deal with here. And this equation, as we just said last time, tells us 2 things. That Vx is directly proportional to cosine theta, and Vx is directly proportional to V naught. And just like the last problem said, hopefully you realized, again, they told us these things are at the same angle. And so because they're at the same angle, this doesn't really matter to us, And all we care about is that Vx is equal to, or excuse me, Vx is proportional to V naught. And so looking at the choices, we see here that the largest launch velocity is D, then A, then B is equal to C. And for the reasoning, well, we've already stated that, at least informally, and so we just need to describe this formally. And so we can say here, according to the equation, Vx equals V naught cosine theta, the horizontal component of the initial velocity is directly proportional to the initial velocity when the launch angle is the same. Important to realize here what you just said, the initial velocity is directly proportional, or the horizontal component of the initial velocity is directly proportional to the initial velocity, is not true if the launch angles are different. It's not necessarily true. It depends on both. But when the launch angle is the same, we see that pure direct relationship. And so essentially, because the angles are the same, this means that the largest initial velocity will produce the largest horizontal component of the initial velocity. And then, of course, just to apply this directly to the situation here, it's crucial, since we're talking about the initial velocity, that we mention, since the object is not accelerating in the horizontal direction at all, the initial velocity, the horizontal component of the initial velocity remains constant throughout the trip. And of course, because they decided to be annoying again, they told us information about the masses of the rocket. And so to fully do this whole question justice, we should just say here, the mass doesn't affect the horizontal speed at the top. And so, of course, a perfectly reasonable question to ask here is, why do they keep giving us the mass if it just doesn't matter? And it's because kids mess that up and they think it does matter. And what the purpose of these sheets are is to try to get you to state whatever misconceptions you may be having, because they want to try to help you get rid of those. And so they give you situations where you have to confront those misconceptions. Now, if there was air resistance, the mass of this thing actually would matter. But if you look at the front cover of the reference table, or the front side of the reference table, there is a box that says the following conventions are used in this exam. And number 2, and this is really the only one that we've gotten to so far, number 2 says assume air resistance is negligible unless otherwise stated. And so since they did not say that there was air resistance or not, we are just assuming it's not really a factor. Take a second to pause this video here and either write this down or amend your explanation, adding anything that you might have missed. And then when you hit play, we'll move on to the next question. So moving on, the next problem on the sheet, on the back side now, is B2RT19, Cannonballs, horizontal distance. I like this question. This is a great question. I want you to pay very close attention to this. It says cannonballs of different masses are shot from cannons at various angles above the horizontal. The different masses part doesn't matter, though. We've established that like 100 times already. The velocity of each cannonball as it leaves the cannon is given along with the horizontal component of that velocity, which is the same. And it says here, rank the horizontal distance traveled by the cannonballs. This is a great question. I want you to take a moment to pause this video here. I would say spend, 6-7 minutes on it. This is a good question. Come up with some reasoning, make your ranking, and explain your reasoning. And when you hit play, we'll go over it. Okay, this is a nice question. Looking at the information given in the problem, there's a lot of important things here. They tell you that the cannonballs are different masses, which is worthless, as we've established already. And it says the velocity of each cannonball as it leaves the cannon is different, which it says that here, next to all the vector diagrams. And it says along with the horizontal component of that velocity, which is the same. And if you look at the diagram here, you notice that the horizontal velocity is the same, 20 meters per second. Interesting. And they're asking you to rank the horizontal distance traveled by the cannonballs. Now, we should be very clear about something in this problem that we have not directly confronted in a conceptual question yet. I think a lot of people look at the answer to this question and see a question that's asking you about the range or the horizontal distance, and they see these 45-degree angles in B and C, and they think, oh, that's what this question is asking about. It's very important to realize what we said about 45 degrees being the angle for the maximum range assumes that the same launch velocity is being used for that analysis. You cannot use this 45-degree launch angle being the maximum range if you're talking about two different launch velocities, because it should be fairly obvious to everybody that even if I shot another projectile at 30 degrees, if we were comparing this range here for the projectile shot at 45 degrees, if we said, well, I shot another projectile at 30 degrees, but I shot it at 4,000 meters per second, it's obviously going to go farther than one shot at 50 meters per second. So this comparison doesn't quite hold up when you're talking about different launch velocities. And so we're just going to have to go ahead and do this the old-fashioned way. Now, they do give us another helpful piece of information, but perhaps you only realize it's helpful when you think about how you would calculate this. Looking at the problem here, they're asking us to rank the horizontal distance. Well, the obvious question when you're looking at these things is what equation is used to solve for the horizontal distance or the range reached by this projectile. And we use the only equation that works in the x direction, because this thing is not accelerating, delta x equals v naught x times t. And what we can realize immediately right off the bat here is that it's actually really helpful to us that they gave us Vx. And not only did they give us Vx, but they actually said they're all the same. And so we can say, since all Vx's are the same, since all V naught x's, that's a little sketchy, but we'll just write it. Since all V naught x's are the same, there definitely shouldn't be an apostrophe there. We can say here that delta x is directly proportional to t. And so essentially, what this question has boiled down to is ranking the times. Because if we rank the times, because the time's directly proportional to the range, we've ranked the range. And so the obvious question here is, how the hell are you supposed to rank the times? There are two ways that you can look at this here. And so I'm going to divide this up into two groups. But the best equation to use is the final velocity equation. Depending on how you look at it, or I should say, not depending on how you look at it, this is going to be the equation to use. And you can look at it two ways. We said here that these projectiles fired at an angle problems have a natural symmetry about them. The time it takes to get up to the maximum height is the same as the time that it takes to come down to the maximum height. And so we can say here like T up equals T down. And so you can choose to just think about the time to the maximum height or to think about the total time. So if you choose to think about the time to the maximum height, you say that the VF is 0, and you would end up with the equation T equals negative V naught Y over AY, and that would give you the time is directly proportional to V naught Y, of course, because AY is a constant. If you chose to consider the total time, then you, again, need to exploit the symmetry given in the problem, which is that if the time up is equal to the time down and the displacement on the way up vertically is equal to the displacement on the way down vertically, and the acceleration on the way up is equal to the acceleration on the way down, then that means whatever velocity this thing is launched with, v naught y, that's going to be equal to the vertical velocity vfy that the object has when it strikes the ground. When we were talking about objects that were thrown up in the air, I was referring to this as the v launch equals the negative of v land concept. There's a symmetry because the acceleration, time, and displacement on the way up and the way down are all the same, or at least have the same magnitude. And so if we use the fact that VFY equals the negative of V naught Y, then we get negative V naught Y equals V naught Y plus AY T. And when we solve for this, we get T equals negative 2 V naught Y, right? Because we take negative V naught Y over here and we subtract to this side over here. And so we get negative 2 V naught Y. V naught Y minus V naught Y is negative 2 V naught Y. And then we put that over AY. And what you see when you use this equation once again is that the time is directly proportional to V naught Y. So notice there are two different ways of looking at it. But what you eventually see here is that the time is directly proportional to V naught Y. And so essentially what you need to do here, and now notice what we just said. The first thing we said is that ranking the distances essentially boils down to ranking the times because they're directly proportional. And because the time is directly proportional to the V naught Y, essentially what this boils down to is ranking the V naught Ys. Because V naught Y is directly proportional to T, and T is directly proportional to delta X. And the important thing to notice here is that they've given you enough information to solve for V naught Y. If you did not realize that, I'd like you to pause the video here and redo your ranking. And when you hit play, we'll wrap up this question. And so notice here for all these problems, they've given you the angle, they've given you the initial velocity, and so using the equation V naught Y equals V naught sine theta can easily be used for all of these problems. And when you do that for these problems, your answers should look like this. So I'd like you to ignore two things about these answers. The first is that I used the subscript I instead of the 0. So V naught Y is shown for all of these variables. There's a missing unit on this one down here, the 34.64. And also, since the initial velocities are given to 3 sig figs, this should technically be given with 3 sig figs as well. So for A, we have 11.6 meters per second. For B and C, because notice those are the same, we have 20.0 meters per second. Notice they have the same initial velocity and the same angle. And for D, we have 34.6 meters per second. Those are our V naught Ys. And so the answer here for the ranking would be D, then B is equal to C, then A. And that's it. Now, of course, the explanation of the reasoning is a little much, but there's a lot of good concepts here in this question. And so we should take a moment to go through the explanation. And so we'll say here first, according to the equation, delta x equals v naught x times t, the range of the projectile directly proportional to the time of flight, since all of the initial horizontal velocity components are the same. Now, of course, we've got to talk about the times here, and we can say according to the equation, and I'm going to go ahead and use the total time version of this equation, and the only reason why I'm doing that is because the range requires you to use the total time in the calculation, and so I'm just going to talk about the total time. Of course, if you did the time to the maximum height equation, it really doesn't matter, because if the time to the maximum height is bigger, that means the total time is bigger. But I'm going to write here, according to the equation t equals negative 2v naught y over ay, the time of flight is directly proportional to the initial vertical velocity component. This means that the object with the largest initial vertical velocity component, and we'll just write down here, because you actually have to use it. Like, there's no point in going through and explaining, and for this problem I did this, and for this example I did this, in terms of the calculations, but we at least should be stating here that, you know, there's a calculation here, we did it, and this is what you're supposed to use. And so using this equation here, we saw that this means that the object with the largest initial vertical velocity component will have the largest time, because they're directly proportional, as we've already established, which means it'll also have the largest range, because they're directly proportional. And just to finish this one up, because they were, again, super annoying, they're giving us masses. And so just to wrap this one up with a little bow, we'll say the mass doesn't affect the range. Take a moment to write that down, or amend your statement to include any of those things you may not have included in your statement. And when you hit play, we'll move on to the last question. Last question here, pretty basic one. It says, B2 RT18, Cannonballs, acceleration at the top. All of the cannons in the figures are identical, and all are aimed at the same angle of 35 degrees to the horizontal. The cannonballs are the same size and shape, but the masses of the cannonballs, as well as their speeds as they leave the cannons, are different. And the question says to rank the acceleration of the cannonballs when they reach their highest point. I'd like you to take literally 1 minute to pause this video, answer the question, and when you hit play, we'll go over it. All right, so this is certainly the easiest question of the day. They're asking you about their acceleration. The acceleration of these cannonballs at their maximum height. It doesn't really matter where they're asking you about their acceleration. They're all the same. Since they only accelerate in the vertical direction, I'll just write here in the y direction, due to gravity, ay equals negative 9.8 meters per second squared for all cannons. Mass doesn't matter. And that's it for the sheet. And because that's it for the sheet, and this is the last thing that we have to do for vertical projectile motion, or projectiles fired at an angle, however you want to call it, that's really it. We are going to use the rest of this video here to talk about an experiment. Okay, so now that we've basically finished all of the new material for projectile motion, we usually spend a day in class on a projectile motion experiment. And the projectile motion experiment is all about doing an experiment where we will predict the range of a horizontally launched projectile. And so what we're going to do here is sort of do that experiment together. Now, of course, I honestly still really haven't figured out how we're going to do a lot of these experiments, but I hope that it'll at least make it clear in this video exactly what we did. And I'll actually show the experiment here in a little bit. So let's ask some questions to begin thinking about this. The first question is, if we are going to measure the range of a horizontally launched projectile, what do you need to measure? Now, again, it's important to realize when they ask you in an experiment, like you're going to do an experiment to figure out the range of a horizontally launched projectile, what you need to realize is essentially what you're doing in an experiment to determine the range is you're calculating it. So if you want to calculate the range of a horizontally launched projectile, what would you need to measure? Think about it. If you were going to measure the range of a horizontally launched projectile, you would need to measure the initial horizontal velocity and the time. How do I know that? Well, it's all about the equation. Remember, we said the key to thinking about any experimental question is to think about the equation. And so those are the terms in the equation, so that's what we need to measure. So in this experiment, I ask everybody to look through their list of materials. They're in a bucket. And what they see in the list of materials is that there is no stopwatch. And so, of course, then, we are going to determine the time it takes for the projectile to reach the ground, but we're going to do that without a stopwatch. How do we do that? In this experiment, what we're going to have is an object being launched off the side of a table, and we need to figure out the time that it's going to take to hit the ground without using a stopwatch. How do we do that? What do we need? To determine the time it takes for the projectile to reach the ground, we can use the free fall equation, square root of 2 delta y over ay, right? Because this thing is launched horizontally, that means the initial vertical velocity is 0. And so when we use the equation delta y equals v naught yt plus 1/2 at squared, that term, the v naught yt term, goes away. And so to solve this for t, we get square root of 2 delta y over ay. So, to ask this question in summary, what do we need to measure? Well, we need to measure the initial horizontal velocity. And we also need to measure the time, but we don't have stopwatches to do that. So we need to measure the launch height. Notice if we just go back to that equation real fast, the acceleration due to gravity, ay, is a number we already know, right? We know that on the surface of the Earth. And so we don't need to measure that. All we need to measure is delta y. So those are the things that we need to measure. And so the obvious question here is, well, how are we going to measure those quantities? Well, measuring the launch height is remarkably easy, right? Because to measure the launch height, you just need to use a meter stick. But the big question here is, how are you going to measure the initial horizontal velocity? And what we're going to use to measure the initial horizontal velocity in this experiment is a photogate. This is the piece of equipment that we talked about when we first started talking about designing experiments for accelerated motion. And when we first started talking about designing experiments for accelerated motion, we showed a picture of the photogate. And the photogate is the device that looks like this. So what I'd like to do here is go ahead and do this experiment and see how it works out. let's go to the lab.
All right, so here we are in the AP Physics lab now, getting ready to do our next experiment, which is all about trying to measure the distance of a horizontally fired projectile. And so you can see here, and I'm probably going to shake the camera a little bit, and I apologize for that. As you can see here in this cup, we have a ball, and here's a ramp. And notice the ramp comes down purely horizontally at the end. When we launch this ball, it's launched purely in the horizontal direction. And so our job here is going to be to try to predict the range of this ball and then confirm our calculations by actually seeing if it goes that far. As we just discussed here in the beginning part of this video, what we need to measure in order to determine the range is the time and the initial horizontal velocity, because the range equation says delta x is equal to v naught x times t. Now, part of what's difficult about measuring the time here, as you just saw, is that the time it takes this thing to hit the ground is really small. And so measuring that with a stopwatch is going to be really difficult. And so what we're going to do, because we know equations for horizontal projectile motion, is we're going to measure the height of the ramp and then use the height to determine the time. And so what you need to do here is take your trusty little meter stick and you need to place it below the ramp here. Notice this thing is right on the floor. And so we put the 0 mark right on the floor, and now we'll just come right up next to this thing and look at the height. Now what you want to do here to accurately measure the height is you want to measure it from the center of the ball. And so what we're going to do is you want to put the ball on the track here and then look at it from the center of the ball. And so to me, in fact, and I know the camera is shaking a lot, maybe I can stabilize it like that, it looks like the center of the ball is at 73.80 centimeters. I think it's right on that line. Now, of course, that's difficult to determine when you're just standing here trying to hold the thing with one hand, but let's call that 73.80 centimeters. Write that down. What we need to do is convert that to meters for the units to work out right in the calculation. So we'll call that 0.7380 meters. And so now we have our height, and we can use that to find the time. We're just going to go ahead and do that calculation separately here. Now, measuring the initial velocity is not going to be as easy. And what we're going to use to measure the initial velocity is this device here. This device is a Photogate. As you can see here, it has a laser, an infrared laser, so you can't see it when it's connected, which shoots out of that hole there. And on the other side, it has a little detector. And so I want to show you how this works. Let me see if I can put this phone in my pocket. All right. So if we plug this thing in, which we have it plugged in here to our digital adapter, if we go ahead and plug this in, then we can tell that it gets power by looking at the light. Whenever anything passes through it, the light flashes. And so essentially what this thing is doing is it's measuring how much time something is blocking the beam. And then the second the thing stops blocking the beam, the light goes off. Now this thing can measure the velocity of an object if we program into the computer how big the object is. And so I want to show you what this screen looks like here. The computer that we're using for this experiment here is this janky old thing. Unfortunately, we don't have the most up-to-date lab equipment in our lab, but this actually works really well. And so when you plug in the Photogate, what you see here is a menu for all of the different options for what the Photogate can do. And what we're going to use is Photogate Timing. Now when you go to the top, you'll see here that it says flag length. If you remember, I showed you when we first talked about the Photogate, I showed you a picture of a cart with what was called a picket fence on it, which is basically like a piece of plastic with these black stripes on it. And when the black stripes pass through the Photogate, they block the beam.
It's also this thing. Since that whole thing is black, when that passes through the Photogate, the whole thing blocks the beam.
We're not going to use one of these picket fences because what's going to be passing through the Photogate is this ball. And so what we need to put in for the flag length here is the size of the ball. Now, of course, the ball is small. And so what we're going to do here is we are going to use a Vernier caliper to measure the diameter of the ball. And the way that you do this is pretty simple. And people tell me every single year that you guys use these in shop. But I'm just going to show this here. We take the ball, we place it inside the jaws of the caliper. And we close it up. And as you can see here, we want to make sure we're doing this in such a way that we're able to get the exact diameter of the ball inside the jaws. And so notice, when we have the inside of these teeth here right on the diameter of the ball, we get a measurement. Now these things, is it focusing? These things are a little confusing to read because as you can see, there's a part of it that says inside and outside. Even though, this is confusing, even though the ball is on the inside of the jaws, that's not what inside and outside means on these devices. What inside and outside means on this devices is the outside diameter or the inside diameter. So notice, I can also use this caliper, say, to measure the opening of this cup here, and see how I have these placed on the inside diameter of the cup? That's what the inside part of this scale is for, because we're measuring the inside diameter of something. If I want to measure the outside diameter, then I put it like this, and then I use the scale that says outside. Okay, so let's measure the diameter of the ball. The first thing to pay attention to here is that, let me just get that centered. The first thing to pay attention to here is that the scale is millimeters. And so what you need to go to first is the part that says 0. You need to go to the part that says 0. And as you can see here, hopefully you can see, the 0 line, see if that focuses again, the 0 line is right in between 12 and 13 millimeters. And so once you see that the 0 line is right in between 12 and 13 millimeters, now you need to go down to the other tick marks to see what the decimal place is. And essentially the way this works is you just have to look at which line lines up, which line on the outside scale lines up with a line on the middle part here. And so if you notice, this 0.1 line right there does not line up with the line below it. The 0.2 line does not line up with the line below it. The 0.31 almost, but not quite. The 0.4 line is what lines up perfectly, not the 0.5 line, as I can see here now pretty clearly, I think. It just went out of focus again. And so we're gonna call that 12.4 millimeters. And so since we need to convert that to meters, we're going to call that 12.4 times 10 to the negative 3 meters. And since 12.4 times 10 to the negative 3 meters is not written in correct scientific notation, then we'll need to write that in correct scientific notation by calling it 1.23 times 10 to the negative 2. Now, we don't actually need to go nuts about the estimating the final digit here, because the Vernier caliper takes care of that for us by using the inside scale and the outside scale. And so when we go to the screen here for flag length, we're going to put in 1.24, and then there's an EE button down here. And if you push it twice really fast, then it shows up E on this screen. And then we'll put -3. And now we have our flag length. That essentially is the part of the ball that is passing directly through the center of the photogate. Now for photogate spacing, because we only have one photogate and we only need one photogate to measure the velocity, we're just going to set that as 0. The time in the gate, we don't really care about. What we care about is the velocity. And so we're going to make that visible and make everything not visible. And then when we're done with that, we can just go back to the home screen and go to the part of this that says digits, and now it's going to give us the velocity in the gate. And if we hit play, now we see some numbers, which is good. And if we pass something through the gate, like my fingers there, just very fast, or I'll do it with the phone, then you can see, even though I hit it, the velocity of the phone passing through the gate is on the screen. And so notice if I do it faster now and don't hit it, then we get a little bit of a faster number. Sorry for giving you motion sickness if you're watching this. Now the crucial part of this experiment, because notice the number we plugged into the computer was the diameter of the ball, we need to make sure that it is exactly the diameter of the ball that's passing through the photogate. And so we're going to use this ring stand to help us do that. And so I'm going to take this thing and I'm going to turn it around, and I'm going to set this up so that the photogate beam is going to cross where the ball goes. And so what we do here is we don't want to obstruct the beam, so we just put this on the outside like that. And we'll tighten this like that for now. We'll make sure this is upright. And then we're going to go ahead and put the ball on the track. Now this is one of the more annoying parts of the experiment because it's tedious work. You kind of just have to make sure that this thing lines up. And we actually want to get this a little closer to the edge of the track because that's where it's reached its full-on takeoff speed. Now it's not going to accelerate after the track gets flat, and so notice here, if I show you this side, you can see we have the gate positioned after the track gets flat, and so that's really all that needs to be done. This part of this is really annoying, and so you just kind of need to put the ball on the track and do your best to make sure that the center of the ball is passing through the center of the beam. Now the obvious question is, well, how the heck do you do that? And it's actually not that hard. What you do is you get a partner, which I don't have here, so I'm just going to try to put something on the track to hold the ball in place. Notice that the red light is on, so it's tripping the beam right now. And we take the caliper, and if you extend the caliper all the way out, it gives us a nice straight piece of metal to use as our guidepost. And so if we hold that at the center of the holes, and we look at it, as you can see here, the photogate is a little too high. the photogate is a little too low. And so if we lower that down a little bit, then we should see the center of the ball pass through the center of the beam. And so now it looks like the center of the beam is passing basically at the center of the ball, and so we're good. And we can do a little test here just to show, and I'll try to get this working as best we can. And we'll take the ball and we'll let it go through the gate. Notice we should see the red light go off. We see the red light go off, and the number is 0.12. And that's a problem, because I've done this experiment a bunch of times, and so I know something is wrong. Oh, duh. Okay, so you'll notice this sometimes when you're doing experiments, and so this is just going to have to be how it goes. Remember I converted this to correct scientific notation by moving the decimal point over once? I accidentally wrote that as times 10 to the negative 3, and that's supposed to be times 10 to the negative 2. Okay, silly me. So we put that in there, and so we put it through one more time, and now we get a speed that seems pretty accurate, because that's usually what it is, 1.20. Now, that trial doesn't count, because that was just the first one, but we're going to let this thing go maybe 10 times and see what the velocities are, and I want you to record them as we're going along, because we're going to take a bunch of velocities and then average them together. And so notice this part of the track is actually really super useful, because it lets me figure out that I'm using the correct height, the same height every time. And if I'm using the same height every time, then I know that this thing should have a consistent speed at the bottom. All right, so here we go for trial 1. 1.20 meters per second, write that down, 1.20 meters per second. Trial 2, 1.21 meters per second. Write that down, 1.21 meters per second. Trial 3, 1.20 meters per second, write that down. Trial 4, 1.23 meters per second, write that down. Trial 5, 1.14 meters per second, write that down. Trial 6, 1.23 meters per second, write that down. Trial 7, 1.23 meters per second, write that down. How you liking those cat-like reflexes on the catch there? So trial 7 was 1.23 meters per second, write that down. Trial 8, 1.24 meters per second. We're hovering around the same value, so we'll stop after 10. Trial 9, 1.23 meters per second. And our last trial, 1.22 meters per second. I'd like you to pause this video here, calculate the average velocity, calculate the time using the height that we got before, and then use that to calculate the range. And when you hit play, we'll see if that's actually the range. Okay, so now we're in the home stretch here. We should have calculated that the final range should be 47 centimeters. And so what we need to do here is we need to take our meter stick, and we need to hold it up to the edge of the table and make sure that it's coming straight down. And then we'll take our other meter stick and put it right next to it. And so notice we can see here that if we look straight down, it's just lined up with the edge of the table and it's straight. And so we'll take our cup and we'll put our cup, the center of our cup, at 47 centimeters. And so we have the center of our cup there at 47 centimeters. And so now we can let the ball go and see if it goes in the cup. Oh, this is so exciting. And notice it hits the side of the cup. And usually when I tell every group to let the ball go and see if it gets in the cup and it hits the side of the cup, they're very disappointed. And there's no reason to be disappointed at all, because that makes sense. That's actually what you're supposed to get. Why are you supposed to get that? I'd like you to take a second to pause this video here and think about why we would expect the ball to come down and hit the side of the cup when we let it go. Why, when we let this ball go, do we see it hit the side of the cup instead of going into the cup? Take a second to pause this video here and think about that. When you hit play, we'll discuss. Okay, so first of all, there's air resistance in this room. And so when we let the ball go, we expect it to be slowed down a little bit in the horizontal direction, because if the ball is moving this way, then that means air friction is moving this way, which is slowing the ball down. And so we would expect it to slow down just a little bit in the horizontal direction, meaning the V0x is going to be smaller. Of course, if the V0x is a little bit smaller, then it's not going to go to the 47 centimeter distance. It's going to go a little shorter than that. But there's a much better reason for why it hits the side of the cup. And that's because when the ball is coming down like this, about to hit the side of the cup, it has an initial, or I guess final, whichever way you look at it, it has a velocity vector which is pointed at an angle down like this. We actually solved the problem trying to find the angle that the projectile has on the way down already. And so because the velocity vector is at an angle, in order to really see if our calculations are correct, we have to tip the cup. And now we have the cup sufficiently tilted. And when we let the ball go here, notice it was a little off center, but it was just about at the cup if we account for air resistance. So that's the idea. Air resistance affects the projectile, and the angle matters at the end of the flight path, but the equations for physics work. And that's the key idea behind this experiment.